For the last 30 years, we've had the benefit of Moore's Law, an incredible phenomenon. Without changing the software, the hardware can continue to improve in an architecturally compatible way. Every single industry has subsequently been built on top of it, but we know now that the scaling of CPUs has reached its limit. The free ride of Moore's Law has ended.
Jensen introduces Nvidia's Blackwell chip as a revolutionary leap in computing, overcoming the limits of Moore's Law. Unlike traditional CPUs, Blackwell's architecture enables accelerated computing by reimagining the entire computing stack, powering breakthroughs in industries like AI, quantum computing, and drug discovery. He highlights the transition from traditional coding to machine learning, where computers analyze vast data to create predictive models. This shift, driven by GPUs, has transformed software development and unlocked new capabilities in fields such as language processing, image generation, and scientific research. Blackwell's design connects 144 GPUs into a unified system using Nvidia's NVLink, delivering massive computational power. This innovation enables unprecedented data analysis across domains, redefining problem-solving and setting a new standard for the future of computing.
There's no memory locality issues, no cache issues. It's just one giant chip. And so when we were told that Blackwell's ambitions were beyond the limits of physics, the engineer said, so what? And so this is what happened. And so this is the Blackwell chip. General purpose computing as we know it has existed for 60 years until now. This at its core is what happened to our industry in the last 10 years. We have now seen a complete reinvention of the computing stack. The whole technology stack has been reinvented. The hardware, the way that software is developed, and what software can do is now fundamentally different. We dedicated ourselves to advance this field. And so this is what we now build. Initially, we were building GPUs that fit into a PCI Express card that goes into your PC. This is what a GPU looks like today. This is Blackwell. Yeah, thank you. A massive system designed to study data at an enormous scale so that we could discover patterns and relationships and learn the meaning of the data. This is the great breakthrough. In the last several years, we have now learned the representation or the meaning of words and numbers and images and pixels and videos, chemicals, proteins, amino acids, fluid patterns, particle physics. We have now learned the meaning of so many different types of data. We have learned to represent information in so many different modalities. Not only have we learned the meaning of it, we can translate it to another modality. So one great example, of course, is translating English to Hindi. Translating English, large body of text, into other English, summarization. From pixels to image recognition. From words to pixels, image generation. From images, videos, to words, captioning. From words to proteins used for drug discovery. From words to chemicals, discovering new compounds, all because of this one instrument that made it possible for us to study data at enormous scales. Well, I just want to say that in order to build the Blackwell system, of course the Blackwell GPU is involved, but it takes 7 other chips. TSMC manufacture all of these chips, and they're just doing an extraordinary job ramping the Blackwell system. Blackwell is in full production, and we're expecting to deliver in volume production in Q4. And so this is basically Blackwell. Now this is one of the things that's really incredible about the system. Let me show it to you. Oh, nothing's easy this morning. This is NVLink, and it goes across the entire back spine of a rack of GPUs. And these GPUs are all connected 72 dual GPU packages of Blackwells, 144 GPUs, connected together so it's one giant GPU. If I were to spread out all of the chips to show you what this connects together, it's essentially a GPU so large, it'd be like this big. But it's obviously impossible to build GPUs that large, so we break it up into the smallest chunks we could, which is reticle limits and the most advanced technologies, and we connect it together using NVLink. This is NVLink backspine. You're looking at all of the GPUs being connected. That's the quantum switch that connects all of these GPUs together on top. Spectrum X, if you would like to have Ethernet, what connects this together, this is connected to this switch, and this is one of the most advanced switches the world's ever built. Now all of this together represents Blackwell, and then it runs the software that's on top. We no longer can afford to do nothing in software and expect that our computing experience will continue to improve, that costs will decrease, and continue to spread the benefits of IT and to benefit from solving greater and greater challenges. We started our company to accelerate software. Our vision was there are applications that would benefit from acceleration. That acceleration benefit has the same qualities as Moore's Law. For applications that were impossible or impractical to perform using general purpose computing, we have the benefits of accelerated computing to realize that capability. For example, computer graphics. Real-time computer graphics was made possible because of Nvidia coming into the world and make possible this new processor we call GPUs. But we felt that long-term, accelerated computing could be far, far more impactful. There is no such magical processor that can accelerate everything in the world. Because if you could do that, you would just call it a CPU. You need to reinvent the computing stack from the algorithms to the architecture underneath and connect it to applications on top. In one domain after another domain, computer graphics is a beginning, but we've taken this CUDA architecture from one industry after another industry after another industry. Today, we accelerate so many important industries. cuLitho is fundamental to semiconductor manufacturing, computational lithography, simulation, computer-aided engineering, quantum computing, so that we can invent the future of computing with classical, quantum, hybrid computing. In each one of these different libraries, we're able to accelerate the application 20, 30, 50 times. Of course, it takes a rewrite of software, which is the reason why it's taken so long. In each one of these domains, we've had to work with the industry, work with our ecosystem, software developers and customers, in order to accelerate those applications for their domains. Modulus, teaching an AI the laws of physics, not just to be able to predict next word, but to be able to predict the next moment in time of fluid dynamics and particle physics and so on and so forth. And of course, one of the most famous application libraries we've ever created, called cuDNN, made it possible to democratize artificial intelligence as we know it. These acceleration libraries now cover so many different domains that it appears that accelerated computing is used everywhere. But that's simply because we've applied this architecture one domain after another domain that we've covered just about every single industry. Now, accelerated computing, or CUDA, has reached the tipping point. The first thing that happened, of course, is how we do software. Our industry is underpinned by the method by which software is done. The way that software was done, call it software 1.0, programmers would code algorithms, we call functions, to run on a computer. And we would apply it to input information, to predict an output. Somebody would write Python or C or Fortran or Pascal or C++, code algorithms that run on a computer. You apply input to it, and output is produced. Very classically, the computer model that we understood quite well. However, that approach of developing software has been disrupted. It is now not coding, but machine learning. Using a computer to study the patterns and relationships of massive amounts of observed data to essentially learn from it the function that predicts it. And so we are essentially designing a universal function approximator using machines to learn the expected output that would produce such a function. And so going back and forth, looking, this is software 1.0 with human coding to now software 2.0 using machine learning. Notice who is writing the software. The software is now written by the computer. And after you're done training the model, you inference the model. You then apply that function now as the input. That deep learning model, that computer vision model, speech understanding model, is now an input neural network that goes into the GPU that can now make a prediction given new input, unobserved input. And we have gone from coding to machine learning, from developing software to creating artificial intelligence, and from software that prefers to run on CPUs to now neural networks that runs best on GPUs.
Nvidia's Blackwell chip marks a major leap in computing, breaking past Moore's law by combining advanced hardware, algorithms, and software to tackle complex challenges across industries. With its interconnected system of 144 GPUs, Blackwell delivers unmatched computational power, transforming fields like AI, quantum computing, and drug discovery. This innovation redefines how data is analyzed, enabling breakthroughs in areas such as language translation, image recognition, and molecular science. The transition from traditional coding to AI-driven machine learning has revolutionized software development, making AI more accessible and impactful across industries. Blackwell embodies this shift, offering a scalable platform that accelerates innovation. Now in full production, it sets the stage for a new era of computing, empowering industries to achieve unprecedented advancements. How do you see AI transforming industries that have been slower to adopt advanced computing technologies? What ethical considerations should guide the development and deployment of such powerful AI systems?